We are live. Hello, welcome back to another NVIDIA developer live stream, joined by two new faces today, Tao and Xiaoming. We're going to be talking about DeepSeek R1 throughput optimizations on Blackwell. Again, this time is for you guys, audience attendees. Ask questions in the chat, wherever you're joining us from, LinkedIn, YouTube, even X. We've expanded our reach. So just bear with us as we corral questions. So appreciate if you guys can take the time, ask questions, and post your anything in the chat. All right. So today I'd like to introduce the new guys. Right. We have Tao. He is an engineering manager on TRT LLM and focused and TensorRT, focusing on deep learning inference optimizations. Most recently on LLM inference for flagship SOTA models like DeepSeek R1 and Llama 4. And next to him, we have Xiaoming, who is a principal architect and senior manager working on TRT LLM performance. So, guys, welcome to our live stream. Say hello.
Hello.
All right, so I think now I'll hand it off to Tao. He's going to get us started. Again, please, if you have any questions, drop them in the chat, and we'll eventually stop, pause, and have either Tao or Xiaoming answer them. All right, Tao, I will leave it to you. I'll bring the slides up.
Okay. Thank you, Zach, for the introduction, and thank you everyone who joined today's session. Today we are going to talk about the DeepSeek R1 max throughput optimization for Blackwell, and the whole work slides are done by NVIDIA TensorRT LLM team, and me and Xiaoming will go through the presentations and answer questions you may have. Let's get started. So before we get started, maybe some of you may not very familiar with TensorRT LLM project. TensorRT LLM is a full open source project published by NVIDIA to focus on large language model inference optimization. And here are some useful links if you didn't know or hear TRTM before. You can see the GitHub and repo and the document here. And also the reproduced steps of those documents today's slides, DeepSeek R1 number are also fully open sourced in the GitHub. You can see the third link. The last one is we also published the one DeepSeek R1 optimization technical blogs previously. If you missed the presentation or live stream today, you can also read the technical blog to see the very detailed explanation on each optimization we did. Hope this can help you to understand how we optimize the DeepSeek R1 on Blackwell, and hope this can inspire some of your work. Thank you. So today's slides content mainly contains about, first we will quickly go through the DeepSeek R1 model architecture, and then we will introduce the engineer optimization implementations, including the MLA layers optimizations, MOE layers optimizations, and then the TensorRT runtime optimizations. Finally, we will summarize our learnings and maybe take questions and answer them. And if you have any questions during the live stream, you can type in the comment section and we will try to answer some interesting one. So part one is model analysis and optimization. Let's quickly recap the DeepSeek R1 model architecture. So DeepSeek R1 has 61 decoder layers, and every layer has multi-latent attention, shorted as MLA here, and it has 3 dense MLP layer plus 58 MOE layers. And for the MOE layers, we can see the structure of MOE in the right side of this slides. For the MOE layers, DeepSeek has one shared expert every layer and 256 rotated expert every layer, and each token will select top 8 shared rotated experts. For the routing part, the DeepSeek paper introduced one new routing methodology calling aux loss-free routing. Basically, it adds some bells to the load balance experts, and also doing the node limited routing means first trying to group the experts into eight groups, and then select the top 4 groups first, and from this top 4 group, select the top 8 experts. The gating score of the MOE is sigmoid plus normalization, and the activation is VGLU. So maybe let's quickly run through the MOE computations. So the MOE is quite different from the MHA communication. Basically, it first trying to do a projection from the hidden state to a lightened state, and then do the up projection from this lightened state to a new tensor, and then do the also do the rope, and then do lastly do the normal SDPA communication, and do the output projection.
We have a question online. How does the load balance change the memory? I think it's a question mainly from how to change the memory footprint, if I understand it correctly. So I think basically I think it doesn't change the load memory footprint side, because just bias and top K selection policy change.
Yes. Okay, let's continue. So based on the MOE computation formula, we found out, and also there are some other community comment in the Flash Infer AI you can reference. It has very detailed analysis on how many flops and how many memory footprint to compute the MOA. So the formula is very kind of complex. I won't go into every details of the formula today, but the takeaway from this formula is that for the context phase, we do not need we should not do the with observe, and for the generation phase, we should do the with observe to save the computation. Let me try to explain how the with observe can change the generation phase MLA. So here is the diagram. In the generation phase, the input hidden state is firstly do down projection for the Q and down projection for the KV and the K root part. And we then do the Q up projection. It means the CQT tensor to multiplied by the WQ and WQR matrix, and then we observe the up projection of K to the WK matrix, means to do the multiplication here to get a QF tensor, and we do MQA for with this QF tensor and the compressed KV tensor, and for the V part, we will do the WKV matrix multiply after the MQA, and after that we do output projection and multiply the output of the WKV to the WO matrix. Previous slide was the with observed optimization. There is also another very important optimization introduced in the DeepSeek model. It's the MTP, multi-token prediction. It's a speculative decoding technique, and based on our silicon environment, you can see the diagram here. For either tensor expert parallel, we call it TEP, or data expert parallel, we call it DEP. For both of this parallel scheme, you can see in the most of point in the parallel curve, the MTP can show great benefit for the curve. Maybe only except leftmost 1 point of the max throughput. So we also implement the MTP in the TensorRT and DeepSeek modeling part, and we encourage you to turn on and use MTP if you are running within the in the middle range of the rightmost range of the parallel curve. And part one was done most about the model part, and part two we will try to introduce the engineer optimization implementation details and what's the performance benefit of each item. Before we go into the details, I want to quickly show the progress of our optimization journey. Right, in the February, the first release, maybe just 1 week after the DeepSeek model release, TensorRT can only run about 2,000 TPS per GPU in the throughput cases, and after we continuously improve the performance, now in the July we can already run up to 5,400 TPS per GPU. Note that the numbers can change if you run with different input sequence lengths or output sequence lengths, or you change the access. The number here is based on 1K, 1K SL, OSL, and the max throughput scenario. And the TPS here only contains the output tokens. If you also include the input context tokens, the values will be even higher. Next, we will go through the optimizations we did for the MLA layers. So the first most important one is the attention data parallel. Based on my study, if we just turn on and off this attention data parallel, it shows almost 400% speed up in very simple tuned cases. The reasoning behind this one is that the MQA in generation phase, due to the width observed we introduced before, if we do not do the attention data parallel, the KV cache will be fully duplicated between GPUs, so that will badly impact the max batch size we can reach. So, and the second one important is the attention kernel optimization. We based on the workload and the problem size, we want to focus on the DeepSeek. We find a bunch of the attention kernel optimization chances, and for that one, we achieved almost 20% speed up. And the third one is the IP8 KV cache. So for this one, based on our measurement, if you just use same concurrency, it can achieve 6% better performance, but it can be even larger, because if you use IP8 KV cache instead of BF16, the max batch size can be even larger after you tune it. The fourth one is the manual Kubla stream tactic tuning, and the fifth one is the gem horizontal fusions. Basically, we fused the 3 gems inside the MLA. We call it fuse here. It's a very natural choice to do this horizontal fusion, and we implemented it as day one as baseline. So I didn't show the performance speed up here. And the sixth one is there are some two-stream optimizations. I will cover the details on the slide 18, because the two-stream optimization are shared by the MLA layers and MOE layers. Okay, so the basic idea behind the MLA kernel optimization are three ideas. First is we are trying to use the 2 CTA UTC MMA instructions introduced in the blackwell GPU, and after this one we can achieve about 1165 tops with BF16, and even higher 1006 600 T-flops with IP8. And the second one is we are trying to overlap the MLA with softmax by interleaved tails in the main loop. And the third one is trying to, since there can be many kernel implementation or many kernel configs for even one problem size, we are trying to fine-tune the kernel selection heuristic based on our benchmark result to find the best kernel for each of the problem size and workload. Is there any new questions? Okay, so
the question is, how does optimization like attention DP and MHA for context help with scaling performance on larger model? The larger model, I guess here means even big than R1. If so, I think for larger model, the memory footprint of the weights will be even larger than the R1. And so the remaining memory capacity is even smaller compared with R1. So if we add attention, so the KB cache room is also limited and reduced. So attention DP will help for this case because it can enlarge the memory, it can enlarge the concurrency or byte size for this case.
Okay, thank you, Xiaoming, for answering that.
No problem. Also, another one is what is the percentage improvement of NVIDIA chip performance to DeepSeek optimization performance? I think it's not apple-to-apple comparison. DeepSeek claim is, I think it's H800, and our current number is B200. So it's not apple-to-apple comparison.
Yeah.
That's it.
Okay, let's continue. So another, this slide shows the IP8 KV cache optimization we did in the 1030M DeepSeek R1 implementation. So our current implementation is that in the context phase, first there is a BF16 BF16 kV, and we try to quantize that into IP8 kV and stored 8. But in the context computation, we still trying to use the BF16 MHA. Note that this use BF16 MHA here. It's just because we are still working on to do more optimization. Use BF IP8 MHA here. It's a work in progress. It's not related to we cannot use IP8 MHA here. And in the generation phase, we will read the IP8 kV stored in the context phase, and we will do a quantization for the Q tensor from BF16 to IP8 and do IP8 MQA. So the benefits of this one is it can compress the KV cache size by almost half and allow larger concurrency. And also we can choose to use IP8 attention kernels compared to BF16 to get better flops. So this slide is about the internal precisions of the IP8 attention kernel. So you can see that the input is IP8Q and IP8 KV cache. First, we do a batch the gem BMM1. The input is IP8 and the output of this BMM1 is dequantized to IP32. And we do the stop max in IP32 to keep the precision. And then do IP4 quantize. And then do BMM2 using IP8 tensor cores. And then we finally dequantize the output to BF16. For the IP8 MQA, we are using our TensorDM developed kernels for Blackwell, and we use the community contribute Flash MLE for Hopper. Here is our accuracy study of the IP8 KV cache. We evaluated it based on GSM 8K dataset, and we also evaluated both IP blockwise IP4 checkpoint and a blockwise IP8 checkpoint, and also the IP4 checkpoint. In all the cases, we see basically there are no accuracy drops on the GSM 8K dataset. Another important optimization inside the MLE layer is the manual cuBLAS kernel tuning. So the problem here we found out is that the default heuristic algorithm in the cuBLAS gem may not be the best in some of the shapes. So our solution is we will find the best algorithm for those specific shape we care offline using profiling strategy. And then we add this algorithm map into TensorDM code. And we are trying to use the cuBLAS provided cuBLAS LT Matmore API, which you can specify the algorithm ID you want to run for given gem. So you can see the red part of the slash. There are two gems can be affected by this algorithm choice. For the rotor gem, after this fine tuning, we can see about 15% improvement. For the fuse A gem, we see even larger. It can have up to 67% improvement. And for the
yes, there's one question online is IP. What's the positioning of the gems? So right now, I think we are currently for all the possible gem input is using IP8 as much as possible, and output it depends on the next layer input. Need to be IP8 or IP16. But one thing exception is for the attention gems. Right now, we are still using IP16.
Yes. Thank you, Xiaoming. And let's continue. So for this Coblas kernel tuning, so after we find some problem sets where Coblas may not have the best default heuristic, we also give this feedback to Coblas team, and hopefully it will improve in the later release of the Coblas, and then we can remove the magnitude heuristic in TensorRT repo later. Also, there is horizontal gem fusion in the MLA. You can see that the input hidden state is multiplied by 3 width matrix WDQ, DKV, and WKR, these 3 matrix, and to do the horizontal gem fusion in the PyTorch, you need to change the width loading part of the DeepSeek model to manually fuse all those 3 widths into one bigger width matrix, and manually do the fusion, and do the multiply the fused matrix with the input hidden state in the forward function.
There is also another question online: is could this method be applied to other neural network architecture outside MLA? I think all the optimization we did on the group gem and MOE group gem, and also the horizontal fusion and the gem side, I think we can apply to other networks as well, as long as this is not MLA specific optimization.
Yeah. Okay. Then let's continue. So the previous section is most about the MOE layers optimization. There is another very important layer is MOE layers. So for the MOE optimization, we have basically at least about 6 items we did for the max throughput scenario. And the first one is the expert parallel. For this one, in the most simple tuned cases, if you just simply turn on and off the expert parallel, we can see the expert parallel can give about 142% speed up. The intuition behind this is that when you use tensor parallel, it will shut the matrix multiply in the k dimension, and in the DeepSeek R1 problem set, the k is just about 2000, and if you use 8 GPUs and shut this k dimension, the k will be just about 256. It will be a very small k, and the small k will causing us to may not fully utilize the tensor cores in some cases and hurt performance. The second one is the router gem optimization. We are trying to leverage the mixed IO gems provided by Coblas and avoid the cost from IP 16 to IP32 in the rotor input. After we remove this cast, the gem can be done in BF16 input IP32 output way, and compared to original pure IP32 gems, in the end-to-end we can achieve about 4% speed up. So the third one is top K kernels fusion. We will go to the details later, but this top K kernel fusions, based on our measurement, can achieve about 7.4 end-to-end speed up. The fourth one is we also did some all-gather optimizations, trying to replace the BF16 tensor to IP4 to do the all-gather to save the communication message size. This can give us about 4% speed up. The other one is a Calas group gem optimization. So the Calas group gem optimization was mainly done for the main latency optimization. We also had one sharing session before about the main latency, but after we integrate a newer version of Calas, we found out it can also benefit the max throughput scenario. It gives us about 1.3% end-to-end speed up. Finally, there are also some two-stream optimization. There are three places we can apply the two-stream optimization. Inside the MOE layer, the shared expert and the rooted expert can be run in two parallel CUDA stream. In the MOE part, there are two places now. There are Q norm and KV norm can run in parallel, and also there are Q up projection and K rope node partition concat operation can be run in parallel.
There is two questions online. The first one is, what do you find the best algorithm for specific matrix chip? I suppose this is for the gems. I think there is a heuristic in Catalyst and Kublas as well, but allow you to find the fastest kernels. How do you have something to add?
Yeah, for this one, I think other than what Xiaoming mentioned, there are built-in heuristics between these labs to find the best algorithm. But in some cases, we find that if this built-in heuristic is not enough, we can try to profile offline. For example, give a problem set, you just run all the possible kernels and select the best one and record the kernel's ID or kernel's config offline. And then you use this recorded kernel ID to run the problem in the runtime.
There is another one, is what is the biggest bottlenecks before implementation of those optimizations? And which profiling tool did you use for diagnose them? For later one, I think it's maybe easier to answer. It's a NVIDIA Insight system. And for the first one is before implement those all the MOE optimization, I think the baseline is very bad. It's a TP8 implementation. And I can't remember exactly the performance number. How do you still remember? I think it's for others optimization. I think it's more than maybe 1.5x or 1.6x. So I think the baseline is really bad.
Yeah, and I think Xiaoming's correct. The baseline version in the February, maybe we measured is just 2,000 TPS, and since in NVIDIA we are trying to optimize all the possible items and trying to achieve higher GPU utilizations. So actually, we didn't try to categorize all the performance issues and say which one is the biggest bottleneck. We try to optimize every item, every issue we found.
Yeah, it's a lot of low hanging fruit before that.
Yeah.
There is another question is for the MOE optimization with expert parallel approach. What do you recommend when batch size is small? For batch size is small, I think for the MOE part optimization, I think they are similar. The difference is the attention part. We still doing the tensor parallel, even though it's a duplicate KV cache. But at that time, because your batch size is small, so it doesn't matter. It didn't reach the memory footprint limit.
Yeah. Okay.
Yeah.
Thank you, Shem. Let's continue. So, in the following slides, I will go through the details of the each item in the previous slides of the MOE layers optimization. First, this two diagram shows what we mean by the router gym optimization. So the baseline is that we need the router gym to output an IP32 loaded to do the top key and other computation. And in the baseline implementation, since the gym output is IP32, we need to cast the input to IP32 also. And later we found out actually there are mixed IO gym API provided by Kublas. So we adopted that and removed this cast. Also, after we changed the IO type here, I think the gym itself can be done from using IP32 tensor core to BF16 tensor core, can also benefit some in the flops. So this slide is about the top key kernel fusion we mentioned before. So here is the diagram on how the tokens are distributed to the expert. So for each token, we first trying to select the top 4 groups from the 8 group, and then we select the top key expert among those 4 group. The naive implementation of this 2-stage top key using native PyTorch API, it will involves about 18 CUDA kernels. So those 18 CUDA kernels, the latency will be about 252 million microsecond, and we found out this is far from the GPU can achieve, and we just fused those 18 kernels to 2 CUDA kernels and reduce the latency of those kernels into about 15 microseconds. Also, in the baseline implementation, there is also extra redundant top key calculation in our first MOE customer mob implementation. Later, we found out the issue and removed this redundant top key. It can further reduce the latency about 62 microseconds. This slide is about the IP4 all-gather optimization. So our baseline before any optimization is that you can see after the IMS norm operation, and the router gem top key optimization, we need to do padding and all-gather to gather all the tokens of all the GPUs into one GPU, and then we need to run the MOE part in the expert parallel way. This all-gather, the first version is done in BF16 precision, and we found out actually we can change the computation order to switch the dynamic quant versus the padding and all-gather, because padding and all-gather does not change any of the precision. It's just send the different tokens to different GPUs. So after that computation order change, the all-gather can all be done using IP4 tensors. This can save about 3.5 x of the tensor size. And after this communication saving, we can see about 4% end-to-end speed up. So this slide is showing where the multi-stream optimization can be applied. So the diagram in the left is that in the MLE layers, you can see after the fuse A gem, there are two IMS norm operation applied to the Q and the compressed KV part. These two operations are not related to each other, can be just run into class stream. And the red diagram is showing in the MLE forward generation function. So you can see the concat operation and the batch gem UKB gem data operation also not related to each other and can just run in two CUDA stream. In the MOE pattern, there are also, you can see there can be two streams. In the stream zero is running the shared expert, and the stream one will run all the operations of the rotated expert. So that's all about the MOE optimizations. So other than the MOE, there are also some Tensati runtime optimizations, which can apply to DeepSeek and other models too. But since those items are done in the DeepSeek optimization effort, so we also list here. But those features are general to all the models basically. So the first one is the overlap scheduler. Basically, this is due to we want to save the unnecessary host overhead to not let the GPU or CPU be idle. So when you compute one batch of the of the tokens in GPU, actually you can schedule the next batch in advance before this batch can be finished. The second one is the CUDA graph optimization. So this one is very useful when the batch size is not big enough, or it's useful in the generation phase, because in the generation phase the number of tokens inside a batch is smaller compared to the context phase. The third one is about some memory optimizations. So since this is the max throughput scenario, we want to increase the concurrency as large as possible. Thus, we need to save every possible GPU memory usage to increase the batch size. So there are three efforts related to this. First one is we are trying to estimate the memory usage in a more accurate way inside the Tensati because when we use PyTorch, the memory usage cannot be known accurately in advance. We need to run through some warm-up stage to get an estimate on the dynamic allocated tensors inside the forward function. So the second memory optimization is we are trying to reduce the MOE workspace size. This one we developed a feature called a chunked MOE. Basically, when you run the MOE layers, when there are many when there are a very large number of tokens input to the MOE to the MOE layer, we will split this large number of tokens into smaller chunks and feed into MOE layers separately. Also, there are some PyTorch memory allocator behavior we want to change, and we are trying to allocate more carefully to avoid memory fragmentation, and trying to delete the tensors as early as possible to avoid unnecessary memory occupation. The third one is we fixed some bugs in our baseline implementation. Basically, if you pass the CUDA stream as default args into some function, it will create unnecessary CUDA context in the process start stage. Thus, this causes unnecessary multiple CUDA context always in GPU 0. For this fix, it can achieve about 5 GB improvement. The last one about runtime is we also did some streaming performance optimization. For this one, it's very important, especially when your TPS per GPU is very large, because we use Python to post-process the tokens generated by GPU to CPU and then to the users. But in Python, we cannot do the multi-thread very effectively because the global interpreter lock. So we did some host-side Python code optimization to optimize the post process of the tokens in the streaming scenario. So we also did some ablation study of the runtime features we presented before. Other than attention DP and expert parallel we presented before, the overlap scheduler itself can achieve about 4% speed up. And the CUDA graph part, if you simply turn on and off this flag, turn on the CUDA graph can give us about 22% speed up. And also there is a CUDA graph padding flag. Turn on and off this flag when the CUDA graph padding is used. It can give us about 12% speed up. That's because the CUDA graph padding will increase the hit rate of the CUDA graph, because if you do not do padding, if the byte size is not equal to the pre-captured CUDA graph byte size, it will just run in the eager mode. But if you turn on the CUDA graph padding, it will pad the input bytes to the nearest pre-captured CUDA graph byte size, so that CUDA graph can be applied. So I think that's all about the details of the linear optimizations. And finally, we want to summarize our takeaways and maybe take a few questions if you have any. So our takeaways is that during this optimization journey, there are many general optimizations can be applied to basically all the models, not only DeepSeek. So first one is the sparse MOE related optimization, which can also apply to models like Llama 4 and QA3, which also use MOE. For example, the expert parallel is very essential when the GMK inside the MOE is small. And also the spectral decoding technique like MTP or equals 3 is still a must to improve the performance in the whole parallel curve. And then the reduce communication overhead part, for example, replace BF16 altogether to IP4 low precision. It can also apply to basically all the sparse MOE models. The second category is the runtime optimization, also apply to all the models basically. For example, the CUDA graph is very essential when you use PyTorch, because the PyTorch flow eager mode can have could have larger host overhead. And the overlap scheduler shall always be used for all the models. Also, there are like low precision KV cache. In our case, currently is IP8 KV cache, can apply all the transformer models. The GIM tuning technique we introduced is also general. And the MQA and the GQA optimizations, our takeaway is that for For the MQA in the max throughput or throughput and latency scenario, the attention data parallel is still a must to save the memory to avoid the keep cache duplicate. For the GQA pattern, the attention data parallel might be better when the number of GPU is bigger than the keep cache head size. Also, there are some number of optimizations are very unique and maybe only can apply to the DeepSeek R1 now. For example, the two-step top K we introduced, and also the MLA with absorb. Since currently maybe only DeepSeek R1 use MLA broadly. And I think that's all the slides we want to present, and we can stay here if you have any questions or topics you want to discuss. And thank you.
Thank you, Tao. Yeah, thanks everyone for joining us today. There are some questions that came through. If you have any more, we can stay on for a few more minutes. Otherwise, this recording is always available on our NVIDIA developer YouTube. We posted the links in the chat, as well as we've got a lot of questions about the slides. They will be available. Give us some time, maybe about 24 to 48 hours, and we'll post them in the description of this video. So I don't see any more questions coming in. And we're kind of at the top of the hour. So just want to thank everyone for joining us again this week. We're going to be quite busy. We'll have another stream tomorrow on the Nemo Retriever, and a few other streams coming up, including our Dynamo office hours ongoing. So I want to thank Tao and also Xiangling for joining us today. Thanks for joining us, you in the audience. Join us next time.
Thank you. Bye-bye.
Thank you. Thank you, everyone. Thank you, Zach.